Welcome to Module 1, Chapter 3, where we focus on closed-loop supply chains, CLSCs. In this chapter, we'll explore how CLSCs fundamentally change the way organizations manage products and materials, shifting from a traditional linear approach to a circular one. This means that instead of products ending up as waste, they are returned, recovered, and regenerated, creating ongoing value. We'll discuss the essential concepts of reverse logistics, remanufacturing, and resource recovery, and examine how these strategies help companies reduce waste, lower costs, and drive innovation. CLSCs are a cornerstone of the circular economy, supporting sustainability by keeping resources in use for as long as possible. By the end of this chapter, you'll understand the strategic importance of CLSCs, how they support sustainable business models, and how they can be leveraged to maximize value recovery and foster innovation across various industries. This chapter is structured to provide a comprehensive understanding of closed-loop supply chains. We'll begin by establishing the foundational concepts and definitions, ensuring clarity on what CLSCs are and why they matter. Next, we'll examine the design and operation of these supply chains, focusing on practical aspects such as network structure and process optimization. We'll then explore material recovery and remanufacturing strategies, highlighting the importance of infrastructure and product design. The chapter also addresses systemic challenges and the need for circularity in design, as well as the enablers and barriers to effective implementation. Real-world case studies will illustrate how these concepts are applied in industry, providing practical insights. Finally, reflective and short-answer questions will help you apply your knowledge to real-world scenarios, ensuring you gain both theoretical understanding and practical skills for implementing CLSCs. Foundations of closed-loop supply chains. Closed-loop supply chains, or CLSCs, are systems that integrate both forward and reverse logistics to transform waste into reusable resources. Unlike traditional linear supply chains, which focus on a one-way flow from production to disposal, CLSCs are designed to recover, regenerate, and reintegrate products, components, and materials back into the supply chain. This approach is fundamental to the circular economy, as it minimizes waste and maximizes resource efficiency. Key practices in CLSCs include reverse logistics, remanufacturing, and resource recovery, all aimed at closing material loops and supporting sustainable business models. Real-world applications, such as those in electronics and consumer goods, demonstrate how CLSC principles can solve business challenges, drive innovation, and create value. Understanding CLSCs is essential for anyone interested in sustainable supply chain management and the transition to a circular economy. Closed-loop supply chains transform traditional supply chains by focusing on product return and material regeneration, moving from a linear to a circular model. Reverse logistics is a key process that manages the return flow of products for reuse, refurbishment, or recycling, ensuring valuable materials are not lost. Remanufacturing restores used products to like-new condition, maximizing value and supporting sustainability. These processes help companies recover resources, reduce waste, and extend product lifespans, making them fundamental to achieving circular economy objectives. By integrating reverse logistics and remanufacturing, organizations can maximize value recovery, reduce environmental impact, and create new business opportunities. Understanding these key processes is crucial for answering questions about how value is recovered and how supply chains are transformed to support circularity. Optimizing closed-loop supply chains, CLSCs, involves making both strategic and operational decisions to ensure efficient product returns, remanufacturing, and network design. In sectors like fast-moving consumer goods and B2B markets, CLSCs add significant value by enabling the recovery and reuse of materials that would otherwise be lost. The integration of Internet of Things, IoT, technology is a major advancement, as it allows companies to collect real-time data throughout the product lifecycle. This data-driven approach improves decision-making, enhances product recovery, and supports sustainability goals by enabling predictive maintenance and resource optimization. IoT also helps companies track products, monitor their condition, and streamline logistics, making CLSCs more adaptable and responsive to market needs. These innovations highlight how digital tools and smart strategies can transform supply chains, making them more sustainable and competitive in a rapidly changing business environment. Design and operation of CLSCs. Legislation plays a pivotal role in shaping closed-loop supply chains, particularly in industries like photovoltaics, where regulations such as EU directives mandate proper waste management and recycling of PV panels. These legal requirements drive companies to develop robust systems for collecting, processing, and reintegrating end-of-life products. Network optimization is another critical factor, as balancing assembly and disassembly lines can significantly improve both environmental outcomes and supply chain efficiency. Additionally, using a mix of virgin and recycled materials in products not only enhances sustainability but also delivers economic benefits by reducing reliance on new resources. These factors demonstrate how policy, smart design, and operational excellence work together to create effective CLSCs. Understanding the interplay between legislation and network optimization is essential for navigating the complexities of implementing closed-loop systems in highly regulated and resource-intensive industries. A holistic approach to closed-loop supply chains means integrating every stage of the supply chain, from product design and manufacturing to collection, recovery, and reintegration. This comprehensive perspective ensures that sustainability and resource efficiency are prioritized across all operations. By aligning supply chain management with environmental and social responsibility, companies can foster collaboration among stakeholders, including suppliers, customers, and policymakers. This approach not only supports compliance with regulations but also opens up opportunities for innovation and value creation. Businesses can develop new products, services, and business models that benefit both the economy and the environment. By managing resources wisely and encouraging cross-sector collaboration, CLSCs help organizations achieve long-term sustainability goals and maintain a competitive edge in a rapidly evolving marketplace. Material recovery and remanufacturing strategies. Material recovery is a foundational element of the circular economy, aiming to extend the useful life of products and reduce dependence on virgin resources. The process involves extracting valuable raw materials, such as precious metals and rare earth elements, from products that have reached the end of their life cycle. Achieving high rates of material recovery requires efficient collection systems, which may include take-back programs, specialized recycling centers, and logistics networks designed for reverse flows. Additionally, products must be designed with recycling in mind, using materials that are easy to separate and process. The benefits of material recovery go beyond environmental protection. It also supports low-carbon technologies, addresses material scarcity, and enhances economic resilience by reducing exposure to volatile raw material markets. Investing in infrastructure and product design for material recovery is essential for companies seeking to build robust, sustainable supply chains. Remanufacturing is a sophisticated process that restores used products to a condition that is as good as new, or sometimes even better. This involves several steps: dismantling the product, thoroughly cleaning and inspecting each component, replacing worn or obsolete parts, and reassembling the product to meet original specifications. The environmental benefits of remanufacturing are significant, as it reduces the demand for new raw materials, lowers energy consumption, and cuts greenhouse gas emissions compared to manufacturing from scratch. In a closed-loop logistics system, products are continuously cycled from consumers back to remanufacturing facilities and then returned to the market, minimizing waste and saving costs. This approach not only conserves resources but also supports business sustainability by creating new revenue streams and reducing environmental impact. Remanufacturing is thus a key strategy for companies aiming to retain value and achieve circular economy goals. Remanufacturing complex products, such as heavy vehicles or advanced electronics, presents unique technical and organizational challenges. Disassembly can be difficult due to intricate designs, tightly integrated components, or the use of specialized fasteners. Managing these processes efficiently requires highly skilled labor and specialized tools, as well as robust systems for tracking parts and ensuring quality. Organizationally, companies must coordinate multiple teams and processes to handle the complexity of remanufacturing operations. To optimize value recovery and improve efficiency, advanced decision-making tools are essential. These tools can help companies assess the condition of returned products, determine the most cost-effective remanufacturing strategies, and allocate resources effectively. Overcoming these challenges is critical for scaling remanufacturing operations and ensuring that valuable materials are not lost, but instead returned to the market in top condition. Design for circularity and systemic challenges. Design for disassembly is a critical principle in circular supply chains, as it enables efficient separation of components and materials at the end of a product's life. By making products easy to take apart, companies can recover high-value materials and reduce contamination, which is essential for high-quality recycling and remanufacturing. Maintaining material purity through clean separation of material streams maximizes recycling efficiency and ensures that recovered materials meet industry standards. Advanced simulation-based design tools allow companies to predict the quality of recyclates and assess environmental impacts throughout the product lifecycle. These tools support proactive decision-making and help integrate lifecycle thinking into product development. By prioritizing design for disassembly and material purity, organizations can significantly improve the effectiveness of the closed-loop supply chains and support broader circular economy objectives. One of the biggest obstacles to circular supply chains is the current market structure, which often makes virgin materials cheaper and more accessible than recovered ones. This economic reality can slow the adoption of circular practices. Additionally, there is often a lack of infrastructure for collecting and processing critical materials, especially in emerging sectors like renewable energy. Overcoming these challenges requires strong partnerships among designers, manufacturers, suppliers, and policymakers. Embedding sustainability from the earliest stages of product development supports large-scale material recovery and remanufacturing. Only through coordinated efforts and integrated design can circular economy strategies become mainstream. Addressing these systemic obstacles is essential for scaling up closed-loop supply chains and achieving meaningful progress towards sustainability. Enablers of effective CLSCs. Digital technologies are transforming closed-loop supply chains by providing unprecedented levels of traceability and transparency. The Internet of Things, IoT, enables real-time data collection across product lifecycles, allowing companies to make informed decisions about end-of-life treatment and resource optimization. In applications like modular smartphones, IoT can predict product degradation and optimize remanufacturing processes, improving profitability and reducing waste. Blockchain technology adds another layer of security and transparency, ensuring that data about product origins, movements, and processing is accurate and tamper-proof. Blockchain also enables smart contracts and incentive mechanisms, streamlining operations and enhancing trust among stakeholders. Together, IoT and blockchain are essential tools for building effective, transparent, and sustainable closed-loop supply chains. Supportive policy frameworks and active consumer engagement are critical drivers for the success of closed-loop supply chains. Regulations such as extended producer responsibility, EPR, and landfill bans create strong incentives for companies to invest in reverse logistics and circular economy practices. These policies ensure that manufacturers are accountable for the entire life cycle of their products, from production to end-of-life management. Consumer awareness and participation are equally important, as effective product returns and proper sorting depend on informed and motivated customers. Without active consumer involvement, even the best-designed CLSCs can struggle to achieve their goals. By combining robust policy support with consumer engagement, organizations can create a strong foundation for sustainable and effective closed-loop supply chains. Innovative business models are essential for aligning economic incentives with environmental sustainability in closed-loop supply chains. Approaches such as take-back schemes, leasing, and service-based offerings encourage companies to design products for longevity and recyclability. These models not only reduce waste but also create new revenue streams and strengthen customer relationships. IoT technologies further enhance resource optimization by providing real-time data on product usage, condition, and location, enabling more efficient waste management and logistics. The most successful CLSCs integrate digital technology, supportive policy, consumer engagement, and innovative business models, creating a synergistic approach that drives sustainable circular economies and maximizes value recovery. Barriers and trade-offs in CLSC implementation. Integrating forward supply chains with reverse logistics presents significant logistical challenges for closed-loop supply chains. Coordinating the movement of products, components, and materials in both directions requires sophisticated planning and management. High startup and operational costs are another major barrier, as companies must invest in new infrastructure, technologies, and processes. The lack of industry-wide standards and technical skills makes it difficult to ensure consistent quality in remanufactured goods, which can undermine customer trust and market acceptance. In niche markets, the absence of large-scale actors and proven business models further complicates the implementation of CLSCs. Addressing these issues requires collaboration, innovation, and a willingness to invest in long-term solutions. Consumer behavior plays a critical role in the success of closed-loop supply chains. Reluctance to return products or lack of knowledge about recycling options can hinder the adoption of circular practices. Balancing economic viability with environmental goals requires systemic approaches and strong organizational commitment. Integrating recycled content with virgin materials optimizes both profitability and sustainability, but this often requires advanced planning, technology, and market development. Inefficient logistics systems can exacerbate these challenges, highlighting the need for investment in resilient and sustainable supply chains. By addressing consumer behavior, economic environmental trade-offs, and the integration of recycled content, organizations can build more effective and sustainable CLSCs. Addressing the complex barriers facing closed-loop supply chains requires coordinated efforts from all stakeholders, including manufacturers, suppliers, policymakers, and consumers. Innovation and adaptability are essential for meeting the evolving challenges of sustainable supply chain management. Collaborative innovation enables organizations to develop new solutions, share best practices, and leverage collective expertise. By working together, stakeholders can unlock the full potential of closed-loop supply chains, making them more effective, resilient, and sustainable. Fostering a culture of collaboration and continuous improvement is key to achieving long-term success in circular economy initiatives. Case studies. Industry applications of CLSCs. HP's Planet Partners program is a leading example of a closed-loop supply chain in the electronics industry. For over 25 years, the program has enabled customers in more than 60 countries to return used ink and toner cartridges for free, using mail-back, drop-off points, or pallet pickup. Returned cartridges are sorted, disassembled, or shredded to recover valuable plastics and metals. HP collaborates with specialized recycling organizations to ensure effective processing and material recovery, creating a robust system that supports circular manufacturing and reduces waste. This program demonstrates how a well-designed CLSC can operate at scale, providing valuable lessons on the structure and processes required for successful circular supply chains. HP employs advanced material separation technology and rigorous quality control processes to prepare recycled plastics for reuse in new products. Analytical and functional tests ensure that recycled plastics meet the same performance standards as virgin materials. These recovered plastics are reintegrated into manufacturing, enabling HP to produce billions of cartridges with recycled content. This closed-loop system not only reduces plastic waste and conserves raw materials but also demonstrates how circular economy principles can be applied at scale. HP's approach serves as a model for other companies seeking to implement sustainable business practices and highlights the importance of quality control, material reintegration, and environmental impact in closed-loop supply chains. Interface's Re-Entry program is a pioneering example of circularity in the flooring industry. The program recovers and recycles used carpet tiles, including those from competitors, to minimize landfill waste. Logistics partnerships with regional recycling allies enable efficient collection and separation, reducing transportation carbon footprint. Interface designs its products for durability, reuse, and recyclability, ensuring that materials retain their value across multiple life cycles. Recovered materials, such as glass backing and yarn, are reintegrated into new products, creating circular value and supporting the company's sustainability goals. This case study illustrates how logistics, product design, and collaboration contribute to the success of closed-loop supply chains. Closed-loop supply chains deliver significant strategic outcomes, including resource conservation, waste minimization, and enhanced environmental sustainability. They also provide competitive advantages by driving innovation, reducing costs, and fostering customer loyalty. Companies like HP and Interface have developed scalable CLSC models that serve as blueprints for sustainable business adoption worldwide. These models support the transition to a regenerative economic system, promoting circular and sustainable practices that can be adapted to other industries. Understanding the strategic benefits and transferability of CLSC models is essential for organizations seeking to lead in sustainability and create long-term value. Closed-loop supply chains are essential for achieving sustainability and supporting the circular economy. By enabling companies to turn waste into resources through return, recovery, and reintegration strategies, CLSCs help minimize environmental impact and maximize value recovery. However, implementing CLSCs is not without challenges. High startup costs, logistical complexity, and lack of standardization can hinder adoption. Overcoming these barriers requires systemic approaches, organizational commitment, and collaboration among all stakeholders. Technologies like IoT and blockchain, along with innovative business models, play a crucial role in optimizing resource flows and improving traceability. Well-designed CLSCs not only conserve resources and minimize waste, but also offer competitive advantages and scalable models for other industries, driving innovation and supporting long-term sustainability goals. Thank you for your attention. Next, we continue with Module 1, Chapter 4,